Good morning. Thank you very much for coming to my presentation. My name is Shichen from Alibaba Group, and I take responsibility of the search algorithm, include ranking, personalization, and so on. Today, I will talk about the Cascade ranking model in e-commerce search for both effectiveness and efficiency. Here is our line. First, I will show the background of our work, the inspiration, and why Taobao search have to do the cascade. Then I will describe our proposed algorithm in detail. And finally are the online and offline experiments and the results. Okay, let's first look at these three pictures. They are pages that we can see very commonly in our daily use apps. The search result in Taobao, a list of goods, and the search result in Google, a list of websites, and the recommendation results of music app of NetEase. So in the big data era, there were many real-world applications like search involve the ranking problem for a very large number of items. So how to rank this large amount of items come to be a crucial problem for the search engine. The formal and practical methods use techniques of statistics and probability theory, such as BM25 and PageRank. In recent years, with the progress and development of machine learning technology, lots of learning to rank methods were proposed, include point-wise, pair-wise, page-wise, and from linear model to non-linear model. These methods transfer the ranking problem into the optimization problem and could effectively improve the ranking quality. However, in many real-time applications, we have to consider more factors besides ranking quality, such as response time and the total CPU cost. That's very important in our scenario. So most large-scale search engines, include Taobao search, will use a two-stage approach, filtering and ranking. In the first stage, most of irrelevant items are filtered out by some cheap features. By some statistical features, it will be cheap. And in the second stage, the remaining items are ranked with learning to rank methods. So come to our scenario, Taobao search, the e-commerce search engine, and maybe the biggest. I want to make our problem more clear. To improve the ranking performance, we are trying to add more and more features and trying to add more and more complex features. From statistical feature to model-based features, from linear model like logistic regression to non-linear model like GBDT and the neural network. Besides that, Singles Day Festival, you may hear of that, is the biggest online sales promotion in China and even all of the world. During that day, there will be 400 million users from more than 200 different countries come to buy goods in Taobao. And due to the promotion, queries per second to the search engine can reach to 350,000, which is over 3 times higher than in usual days. So all of the above means that there will be a great amount of computation online. And the computation will take time and take CPU cost. Previously, we have 3 ways to deal with the problem. First, of course, we may add more servers, but it's very expensive. And it cannot solve the problem of response time, response latency. And second, we may lower the ranking item by filtering more items in the first stage. And second, we may drop some costly features, though they are useful, but they may be costly, so we drop them. The later 2 methods sacrifice the ranking quality. So we want to find a sounder way to balance effectiveness and efficiency, so the Cascade ranking algorithm is proposed. Now I will review some related works briefly. There are some valuable private research considering the ranking efficiency. Some of these works employ a feature selection process before ranking, and the others follow the idea of cascade learning. Cascade learning was first proposed for problems such as visual object detection. This method allows most of the background regions to be discussed quickly while consuming most computation on promising object-like regions. And this algorithm, the cascade learning, has also been applied in the ranking applications. Some of the research applies the Booster-style framework with 2 functions. In each stage, one function prunes the input, and the other refines the rank order. An alternative to the Booster cascade ranking framework is a noisy and probability approach, in which whether item can go from a stage to the next depends on simulated probability rather than threshold. Okay, we call our algorithm as CLOES, which is short for cascade ranking for operational e-commerce search. And we mainly concentrate on 3 factors. First, how to balance the ranking effectiveness and efficiency. Second, how to ensure user search experience. Search experience here mean 2 things. The search engine should respond in limited time, and the user should get frequent response item. And third, we should consider more than one factor in e-commerce search, something like click-through rate, conversion rate, and the total GMV. We have to consider multiple factors, more than one factors. And the figure on the right is the general view of our algorithm. The user first types the query, X relevant items are recorded, and then multiple stages are processed sequentially. In former stage, low-cost features are selected for filtering some easily distinguishable negative sample, and more complex features are gradually selected in later stages. And in the final stage, the remaining items are ranked. In the picture, there are 3 stages, but actually there may be 4, 5, and so on. And we try to optimize it, but not in a heuristic way. We formally describe our problem as a 2-class classification problem in a standard learning to rank setting. And capital A here stands for all items in the data set. When users submit a query queue, a subset of A queue will be recorded. Then there are MQ items in A queue. For each item query pair, there are some features Xi to describe it. Different features will cost very differently. For example, a statistic feature like the sales volume will cost less, but for some model-based features like GPT and the neural network, it may cost very much more. And then we can get the whole training set of n instances. Each instance is a tribal consisting of the query Q, the item feature X, and the label Y. Label Y here belongs to 1 and 0, denoting whether the instance is positive or negative. The whole ranking procedure are divided into several separated stages. In each stage, part of the features are selected to calculate a probability, which tells whether the item can go pass through. Equation 1 denotes in equation 1, Q denotes the query, X denotes the item, and J denotes the stage. The probability is calculated by a sigmoid function of selected features. This is the probability of an item can go through from a certain stage to a next, and it's only one stage. So a positive instance means that the item can pass through all stages, so it's a product, such as equation 2 and 3. Okay, now we can get the first loss function. It's a log likelihood and adding a L2 norm. L2 norm here is in case of ill condition, because in real applications, the features are more or less correlated. With this loss function, some of the computation may be saved, because most of the items are filtered out in the former stage, and only a small part of the item will survive to a later stage with more complex features. If we apply the model as last page described, we may lower the amount of calculation, but we cannot control how much calculation we can be saved. So we further get the exact calculation amount into our model. The total CPU cost can be formalized as equation 7. It's the sum of cost of all stages. Each stage cost is a number in the stage time times cost that a single item will take. So the expected number of item count in a certain stage can be calculated by equation 5 and 6. Thus, we can get a new loss function by adding the CPU cost. There are three parts: the likelihood, the normalization, and tau W means the total CPU cost. The bigger the beta is, the CPU cost may be lower, but the performance may decrease too. And if the beta is small, the performance may be better, but the CPU cost may be higher. Though the total CPU cost can be saved, but for a single query, the computational cost may still be high, especially for popular queries, for hot queries. This may result in a high query latency. So, considering the user experience, we further add two limitations, two constraints to the task. First, under each query, the latency should not exceed a given time, and for user, the return items should be no less than a given amount. We model these two limitations to constraints with a hinge loss as described in equation 9. But considering it's a non-differentiable function, we find the approximate differentiable function to replace it, and the optimization can be done easier with gradient methods. The approximate functions are listed in equation 10, and we also can find it in the left figure. So we can get a final loss function. There were 5 parts: the log likelihood, the norm, the beta stands for the total CPU cost, and 2 constraints for the user experience. The last thing we have to consider is that in e-commerce search, we have to pay attention to multiple factors. Pay attention to click-through rate, and the conversion rate, and the total GMV. So we assign each instance in the training set with a weight, denoting how important the instance is. In general, a purchase instance is more important than a click instance, and the expensive instance is more important than a cheap instance. Expensive and cheap here means the item price. So after the algorithm description, we come to the experiment part. We do experiment both offline and online. The offline data set is joined from online log in date October. About 1 day, there were 2 mini instances with 20 features, and 80 to 20% cross-validation is executed for offline comparison. And the online comparison are based on standard A/B testing. Users are hashed into different buckets by their user nick, and 5% of the users are selected for the test. Some features we used are listed in this table. Some statistical features, such as sales volume, will be get very easily and cost very less. And some model-based features are useful but cost much more. Query-only feature is a very special kind of feature. It will not affect on the rank order, but it will change the probability of each stage. Here is the first result of the offline comparison. Logistic regression with 4 features got the highest AUC, but it takes too much CPU cost, so we cannot apply it online. And the logistic regression with very cheap features got the lowest AUC, but the CPU cost is only 6% as using all features. The two-stage approach is a previous method we used online, and the AUC of the two-stage approach is 0.76 in the middle of the above 2 methods, and the CPU cost is in the middle as well. We tried our algorithm CLOES with different value of beta and choose 2 results to be listed here. The beta is set to 1. When the beta is set to 1, the CPU cost is similar to the two-stage approach, but the AUC improved a lot. When beta is set to 10, the AUC is similar to the two-stage approach, but the CPU cost is much lower. So from this experiment, we can conclude that the CLOES can achieve a nice trade-off between accuracy and the CPU cost, which is much better than the two-stage approach, which we used for years. And this page is the online result. Picture on the left record changes of the search latency when we uninstall CLOES. In particular, the CLOES was shut down in 2 steps. First, a small portion of the search traffic is switched to the two-stage approach for gray testing. And after about 20 minutes, the CLOES is fully turned off. So it can be from the figure that there were 2 obvious rising of the latency curve, which respect to 2 steps, and the latency increased from about 60 milliseconds to 21 milliseconds. From the right table, we can observe that the CPU cost of all variants of the CLOES is 20% lower than the two-stage approach, as beta is set to 5 for favoring an efficient solution. The first line, in the first line, is a variance without distinguishing the click behavior and the purchase behavior. So CTR increased a lot, but the number of orders and the GMV decreases. The second line, in the second line, the purchase instance is paid 10 more attention to a click instance. So we can see the CTR decreases, but the number of order increases, but the total GMV is also decreased because the item price is very lower. When we pay more attention to the item price, number of orders decrease and the unit price will increase. And the GMV first increase and later it will decrease. So which setting is the best? I cannot tell. It depends on the context. If the GMV is your main goal, the first line may be a good choice. And if you concentrate more on CTR, the first line is maybe a good setting. This figure shows the comparison result of user experience by queries with and without modern user experience. Hot queries are listed in the left, and long-tailed queries are listed in the right. In each bar pair, the left one is from the Cascade method without modern user experience, and the right one consider user experience. The top sub-figure presents the results of average query latency and the variation of escape rate. Escape rate means that the percentage of users who immediately leave the search page. With modern user experience, query latency can drop a lot for hot queries. According to this, escape rate can decrease about 3% to 5%. And the bottom sub-figure show the result of item result of each query and the variation of the query CTR without escape queries. With modern user experience, result count can increase. Thus, the CTR on the long-tailed queries can improve from 1% to 12%. The overall CTR improve are curved in red. For both popular queries and long-tail queries, the overall CTR increased by 2 kinds of user experience modeling. Finally, we come to the conclusion. A CLOES, so far as we know, is the first piece of public research and a thorough study of designing and deploying a Cascade model in large-scale operational e-commerce search engine, which deals with hundreds of millions of user queries per day with hundreds of servers. An extensive set of experiments and detailed discussion are provided to show that the proposed solution provides a good trade-off between search effectiveness and efficiency within operational environments. There are several possible future work. First, each classifier here is a very simple linear model, while more complex models may be involved. And second, the current approach follows the standard supervised learning, which may be extended to the reinforcement learning setting for modeling both immediate reward and the delay rewards. Thank you very much for your attention. And are there any questions?